Inside a Long Island hangar in 1944, fluorescent bulbs throw cold light across rows of riveted aluminum. A fuselage moves on its dolly, suspended between two men who coax it past a bank of jigs. A rivet gun stutters like a metronome. At one station, a woman checks a stack of color-coded work cards, yellow for the empennage, blue for the wing spars, red for fuel system checks, and slides the next card into place. Crates stamped R2800 wait at the end of the line, their wooden slats branded with the name Pratt & Whitney. Somewhere beyond the bay doors, an engine will be poured into the cradle, cables will be torqued, and the aircraft, bulky and unlovely, will roll out toward a run-up pad as mechanic's thumb ignition switches and oil pressure needle climbs. This is Bethpage. This is Grumman's plant not as romantic workshop, but as a machine whose teeth are people, tools, jigs, and charts. The F6F Hellcat that comes into being here will be heavy where its Japanese rival prized lightness. It will be armored where the Zero was skin and seam. It will look wrong to men who thought the future belonged to finesse. And yet, in the months that follow, that apparent awkwardness will become a new kind of strength, not just in dogfights, but across fleets and skies shaped by radar, doctrine, and an industrial system designed to sustain war on a scale the Pacific had not seen before. They laughed when they read the specifications. That is part truth and part theater. In September 1943, Japanese intelligence and even frontline pilots in the Pacific glanced at the Hellcat's weight, its armor, its 6 heavy Browning .50 caliber machine guns, and concluded in private notes and amused briefings that this was another lumbering American attempt, a blunt instrument against the nimble A6M0. Lieutenant Commander Saburo Sakai, one of Japan's most celebrated fighter pilots, later described that first reaction as disbelief mixed with a kind of amused contempt. The very idea that a plane twice the Zero's weight could outmaneuver or outlast a well-flown Japanese fighter felt, at that moment, unlikely. That contempt was understandable in context. The Zero had been born of a design philosophy that prized low weight, long range, and unmatched turning ability. Designers stripped armor and heavy fuel lines to squeeze every ounce of maneuverability from the airframe. The result was a machine that, in the right hands and in close-in dogfights, could outturn almost anything it faced. Japanese training emphasized gunnery and tactics that took advantage of that turning dominance. Early in the war, American pilots learned that to attempt a flat-turn duel with a Zero was to court disaster. But the Hellcat was not built for flat-turn duels. It was engineered for energy, for altitude, climb, and the ability to trade speed for position. Its power plant, the Pratt & Whitney R2800, was a radial engine designed to deliver sustained horsepower across a broad range of altitudes.
The numbers on paper are less important than what the engine allowed: rapid climbs, higher top speeds, and the reserve to accelerate out of harm's way. Where a Zero relied on outturning an opponent, a Hellcat could climb above, accelerate past, and dive through with concentrated fire, then use its sturdier structure and armor to survive what a Zero could not. On the Bethpage shop floor, these design choices are visible as manufacturing realities. Armor panels are nested into fuselage skins before the wings are mated. Self-sealing fuel bladders are fitted in their bays and pressure tested. The guns, 6 M2 Brownings, come down the line in boxes, mounted and aligned, muzzle cups covered in grease. Each aircraft proceeds not as a bespoke object crafted by a single artisan, but as the result of a choreographed system. Stamping presses, drill jigs that ensure parts match every time. Sub-assembly islands where wings are completed and then swung into place as a unit. The line is organized to minimize wasted motion and to keep entire components interchangeable from plane to plane. Interchangeability is the quiet revolution here. Where pre-war craftsmanship celebrated the hand-fitted part and the skill of one man making one airplane perfect, wartime production demands that if a wing from Station 7 goes on Plane A, it will also fit Plane B without rework. That means tooling, gauges, and a cascade of procedural forms. The color-coded work cards that tell each station worker exactly what to do and in what sequence, with tolerances and torque values printed in clear type. It means that an engine cowling made on one machine will accept an exhaust flange machined miles away. The factory's war is against variability. At the center of that war sits the R2800 crate. To a pilot, the crate is a promise of power. To the shop foreman, it is a fulcrum of supply and rhythm. Engines must arrive on schedule. Missing a power plant threatens to split the cadence of the line. At peak output, contemporaneous accounts reported an assembly cadence that approached one completed aircraft per hour. Assembly cadence indefinito. Whether the figure is literally 1 per hour or slightly different, the point remains. The plant is running as a clock. It is not romantic, it is relentless. And the people are part of the mechanism. Men and women work 3 shifts against the clock. The morning crew bolts in landing gear. The midnight crew fits radio gear and installs instrument panels. Their union is ephemeral, human skill plugged into jigs and charts. Archival testimony from employees, anonymous in many oral histories, remembers the rhythm, the clack of rivet guns, the smell of machining oil, the quiet satisfaction when a test run shows oil pressure and magnetos firing clean. Those are small victories repeated thousands of times until the machine of production hums without pause. This industrial heartbeat is the prelude to something else, doctrine catching up to hardware.
On carriers hundreds of miles away from Long Island, new radar systems and the Navy's fighter direction tactics are beginning to change how air battles are fought. Radar operators locate incoming raids. Fighter directors vector divisions of Hellcats onto intercept headings. That external nervous system multiplies the value of each aircraft leaving Bethpage. A high-performance engine, an armored hull, and a radar vector combine to let a Hellcat climb on a bomber formation, use speed to peel away and attack escorting fighters, and return to cover. A chain of actions that privileges energy and coordination over pure turning ability. The first blows of that combination are not immediately obvious. In isolated fights at Marcus Island and Wake, Japanese pilots encounter Hellcats that do not play by their expectations. Instead of entering the classical turning dogfight, Hellcat pilots climb and use the vertical plane, hammerheads, zoom climbs, and slashing attacks from above. The Hellcat's extra weight becomes kinetic energy available for offense and escape. Petty Officer Yoshio Fukui and others reported being surprised not by an airframe's inability to turn, but by the way it refused to be forced into a turning fight at all. The Hellcat would trade height for position, deliver concentrated .50 caliber fire into vulnerable structures, and then use sturdier armor and self-sealing tanks to survive the return. Tactically, this shift is less about one aircraft being better in every category and more about a mismatch of philosophy. The Zero's virtues are enormous in a fight of sustained tight turns. The Hellcat's virtues are dominant when fights are fought in energy terms, climb, speed, and diving engagement. Another factor tilting the scales is sheer volume. An airframe that is straightforward to produce, maintained by standardized parts, and supported by a supply chain of replacement components does not have to be flawless to be effective. It has to be available when and where doctrine demands it. We can see the consequences in the field, and we can measure them in the margins. Dogfights are not clean mathematical proofs, but by late 1943 and into 1944, the pattern is emerging. In small, brutal engagements, the Hellcat's design and the Navy's evolving tactics begin to yield local superiority. Pilots who survive these fights carry their impressions back to squadrons ashore and afloat. Anecdotes accumulate. A division of Hellcats climb to meet incoming fighters and finds that headed attacks break the rhythm of Japanese formations, that sustained firepower from 6 heavy machine guns can shred a fragile fuselage in seconds, that a tougher airframe returns to its carrier after being hit in places where a zero would have been lost. Back at Bethpage, paperwork keeps score in different units. Thousands of man-hours, shift rosters, parts requisitions, and the quiet, necessary list of what must be reordered when an engine or gun barrel wears.
Production problems that look trivial on the engine bench can become strategic vulnerabilities at sea. A delayed batch of self-sealing tanks means fewer serviceable aircraft for a week. If the engine supply falters, the carrier wings wait. And so managers measure not only throughput, but reliability. It is better to produce a slightly heavier, reliable plane in numbers than a lighter plane that becomes a logistical nightmare. The contrast between design philosophies becomes a running argument between engineers and pilots. On one side, Japanese practice had produced a fighter optimized for individual pilot skill, extended range, and maximum maneuverability. On the other, American practice increasingly accepts extra weight and armor as a trade for survivability and concentrated firepower, but crucially, backs that choice with an industrial model that can maintain, repair, and replace at scale. By late 1943, those two approaches collide in the kind of engagements that carry consequences beyond a single dogfight. The battle narratives that follow make this collision visible. At Marcus Island and Wake, small numbers of Hellcats push back attacks and inflict losses that are disproportionate to their numbers. These were not yet the decisive campaigns, those come later, but they were the testing ground. American pilots learned to exploit climb and speed, to use altitude as a currency, and to hunt in pairs and divisions. The Navy's decentralizing of fighter direction, placing trained controllers on carriers with the power to vector aircraft into optimal interception boxes, removes some of the initiative from lone aces and places it in systems. The result is a multiplication of effectiveness. A Hellcat flying with a clear direction and proper support can be far more dangerous than an equal technical match in a fight of improvisation. But those safer systematized victories are a process, not a guarantee. Japanese pilots still possess formidable skill. Warrant Officer Hiroyoshi Nishizawa, among the ace pilots cited by Japanese records, remains a lethal adversary. Early skirmishes force both sides to adapt. Japanese doctrine is not immutable, neither is American practice. The difference is in capacity. Japan's training pipeline struggles to keep pace as losses mount, while the United States pours resources into pilot replacement, carrier availability, and the factory lines that make the pouring possible. The human element, the pilots, feels each shift keenly. Accounts collected after the war describe a slow erosion of confidence on one side and growing, if costly, assurance on the other. Elders of naval aviation on both sides later framed these months as a turning point in aerial philosophy, an era of the individual virtuoso giving way to one of systems and coordination. It is a cultural shift as much as a tactical one. And yet, the machines themselves retain a kind of blunt poetry. Walk a Hellcat down the ramp at dawn, and notice how its broad wings carry the weight of the design compromise. Enough wing area to keep handling manageable, enough armor to survive hits, enough fuel to reach a target and return. The 6.50 caliber guns are not elegant, they are volumetric. They deliver massed lead into a target in the hope of breaking structure or starting fire. In an age when a single well-placed burst could end an airplane's life, massed firepower and survivable structure together change the calculus of engagement. By the time the first squadrons of Hellcats begin to arrive in theater, Japanese assessments must be revisited. That laughter at specifications, the early, almost reflexive dismissal, gives way to guarded reports and operational notes that scratch at the new reality. This plane is different, not because it turns better, but because it arrives in numbers, endures damage, and operates inside an expanding system of radar and fighter direction that denies the enemy their preferred scope of engagement. The factory, of course, keeps running. A Hellcat that survives a mission returns to a carrier deck scarred but repairable. If it cannot be fixed afloat, it will be cannibalized for parts and sent to a rear area depot. These cycles of repair and replenishment are the silent spine of the war. In one direction sits the design, armor, engine, guns. In the other sits the supply chain, spare tails, replacement engines, trained mechanics. At Bethpage, those supply chain needs are visible under fluorescent light. Crates of fittings, long perches of rivet stock, whole racks of replacement radio sets. The thing that makes an aircraft truly useful in 1944 is not only the strength of its engine or the thickness of its armor, but the predictability of its parts and the speed with which they can be returned to service. Some numbers illustrate this relationship, but numbers are arguments, not answers. By war's end, the United States will have produced on the order of thousands of Hellcats, roughly 12,000 according to several production histories, a figure that signals not just the plane's popularity, but the scale at which Grumman and its subcontractors were able to operate. Hellcat production totals indefined. Equally important, though harder to count, is the rate of replacement. The tempo at which battle-damaged aircraft became serviceable again, the flow of engines from depot to front, the hours mechanics put in under blackout curtains to bring a plane back to fighting trim. Those logistical rhythms resonate with strategic consequence. The Japanese system, brilliant earlier in the war for designing a plane like the Zero, couldn't match the distributed manufacturing, repair depots, and resupply lines that the U.S. produced by 1944.
This was not a moral failing so much as a structural one. Decades of industrial policy, geographic distance from supply sources, and wartime attrition of skilled workers reduced Japan's ability to replace losses at the speed the conflict demanded. To put it plainly, industrial capacity became a weapon. Still, machines do not win alone. The Hellcat's design choices required doctrinal changes to be fully effective. Enter the concept of energy fighting. A simple definition is useful. Wing loading and power-to-weight ratio determine how an airplane converts engine power into climb and acceleration. Wing loading is the weight the wing carries per unit area. The higher the wing loading, the faster the plane tends to be in straight line, but the less tight its turn radius. Energy fighting means leveraging altitude and speed, that stored energy, to gain positional advantage rather than attempting to outturn an opponent. It is less romanticized movies close-in ballet and more chess of altitude and velocity. When Hellcat pilots embrace energy tactics, they force Zeros into a problem. A Zero may be able to turn inside a Hellcat, but if the Hellcat refuses to engage in that plane, the Zero's strengths are neutralized. Worse, when the Hellcat's heavier structure absorbs hits a Zero could not survive, the attrition equation shifts. Over time, the number of Hellcats, the doctrine of fighter direction, and the attritional capacity of sustained logistics create a multiplier. Not because a Hellcat is invincible, but because it is survivable and available. The first exchanges that prove this are gritty and small-scale. At Marcus Island and Wake, American pilots and their commanders begin to see the contours of a new advantage. In oral histories and action reports, pilots describe climbing to meet enemy formations, trading the turn for the vertical, and using concentrated .50 caliber fire to break up tight formations. These are not glamorous set pieces. They are disquieting moments that force fast learning. A pilot who survives such a fight files a report. A squadron leader changes a training brief, and a carrier air officer rewrites intercept procedures. Each small doctrinal adjustment spreads through the fleet with the same efficiency as a workflow instruction on the Bethpage floor.
By the end of these initial encounters, the question is no longer whether the Hellcat can turn with the Zero. It can, to a degree. The question is whether a Zero could impose its preferred fight on American pilots when the latter are flying in coordinated units with radar direction and a steady stream of replacement aircraft. The answer is increasingly no. This is where psychology enters.
The term Hellcat psychosis circulates in after-action debriefs and veteran recollections, not a clinical diagnosis, but a shorthand for an effect noticed by both sides. The sense that the Hellcat fights differently and that sustained exposure to its tactics changes how pilots evaluate risk and engagement. For Japanese aviators, repeated encounters with heavier, better protected opponents that do not conform to classic dogfight templates erode confidence. For American pilots, seeing companions and aircraft survive hits that would have been fatal in earlier campaigns steals a certain operational aggressiveness. Confidence is not a trivial currency in air combat. It shapes willingness to press advantage and to trust coordinated tactics. And still, the human cost is severe. Every repaired plane once bore a man inside who did not return. Colonies of mechanics and medics emerge in the wake of carrier wings, as vital as the manufacturing plants that produced the aircraft in the first place. Bethpage and its sister plants are therefore both factory and infirmary for the air war. They produce the tools that will be used in battle, and then they are part of the apparatus that replaces what battle breaks. The narrative up to this point sets the stage for a larger confrontation. The factory's rhythm pounds out a simple, effective formula. Design for survivability and maintainability, produce at scale, support with radar and doctrine, and feed an attritional engine that, given time and resources, breaks an opponent's capacity to stay in the fight. The first echoes of that formula appear in the small raids and engagements that make pilots rewrite tactics and carriers rework fighter control procedures. But that is only the prelude. The coming months will test whether an industrial system, translated into numbers of aircraft, repair capacity, and doctrinal cohesion, can indeed alter the course of entire campaigns. As squadrons built and trained on the new doctrines prepare to face larger formations, the scene shifts from isolated skirmishes to carrier task groups with more sophisticated coordination. Radar pickets, fighter directors, and the raw arithmetic of planes available for sorties. Commanders like Admiral Mark Mitcher are beginning to grasp that their tactical advantage will rely as much on production rhythm and on individual brilliance. In the hold of each carrier, there will be spare propellers, replacement guns, and men skilled at restoring battle-damaged aircraft to flying condition. In the supply districts ashore, crates from Bethpage move by rail and ship toward the fleet's rear areas. Yet, this is where the story thickens. For all the system's promise, nothing about war is guaranteed. Weather can ground an intercept. A radar operator can miss a vector. A pilot can make a fatal error. The Hellcat is a tool that must be used within a larger human and technical apparatus. Its success requires rhythm, the Bethpage cadence, matched by discipline at sea. Where one link falters, the system stumbles. In the months ahead, those links will be tested on a much larger stage. Carrier groups will face massive Japanese formations and will have to apply fighter direction and energy tactics under fire and confusion. The next phase will not be decided in the Bethpage hangar alone, nor in a single dogfight, but in the interplay between assembly lines and combat decks, between supply manifests and intercept orders. The tale that began under the hum of fluorescent lights will move out into wide ocean and into engagements whose scale will expose the real strengths and limits of an industrially born fighter. For now, the plant continues its cadence. A fuselage becomes a plane, becomes a weapon, becomes a return-to-service statistic. The laughter in Japanese briefing rooms gives way to briefings that demand re-evaluation. Men and women on the shop floor do not see strategic consequences in the rivets they place, but history will count their exertions. The first shocks have been felt at Wake and Marcus Island. The next waves will test whether production and doctrine together can turn those shocks into sustained advantage. The factory keeps beating like a metronome. Outside, the ocean widens, and the distances commanders must shepherd across it grow ever larger. Inside Bethpage, the work goes on with the same small certainties: torque values, rivet counts, and the brisk exchange of one color card for the next. The planes that leave this machine of men and tools will not, on their own, decide any campaign. But by the spring and summer of 1944, those aircraft and the systems that produced and directed them begin to interact in ways that reshape the air war over the Pacific. June 1944 brings that interaction into brutal focus. In the Marianas, carrier task forces on both sides confront each other across a sea of cloud and radar blips. The American carriers are not simply sending up better aircraft, they are sending up wings that are trained to fight together, vectored by controllers using radar to place them at the optimal height and time. Fighter direction is no longer an ad hoc business of pilots spotting smoke and guessing. It has become a coordinated choreography where controllers hand off interceptions like relay batons. When thousands of feet of altitude and a few dozen miles of radar separation are traded for positional advantage, the fight looks different. The engagement over the Marianas, what contemporaries would later call the Marianas Turkey Shoot, is not a single clean set piece, but a cascade of interceptions, failed Japanese strikes, and lopsided exchanges. Hellcats climb into boxes laid out by fighter directors.
They arrive in formation, with reserve energy, and they meet waves of Japanese aircraft, many of which have been launched under rushed conditions, and with crews whose training and operational tempo have been exhausted by attrition. The result is a string of encounters where the American doctrine of energy fighting and fighter direction neutralizes the Zero's classical strengths. Japanese losses in the operation are severe, numbered in the hundreds, and the scale of those losses sends a shock through the Imperial Navy and Army air services. Loss and kill counts indefino. See production notes for verification. The story on that day is the convergence of several forces: the Hellcat's ability to climb and accelerate, the 6.50 caliber guns that deliver a volume of fire lethal to lightly protected airframes, and the system that brings those aircraft to the fight when and where they matter. In the debacle's aftermath, pilots and staff officers on both sides file reports that look less at romance and more at arithmetic. The Japanese find themselves facing not just enemy fighters, but an enemy logistics and command structure that delivers those fighters in waves and sustains them afterwards. Among the American pilots who exemplify the new era is Commander David McCampbell. He is characteristically laconic about his own exploits, but his missions make a point about the interface between individual skill and system support. Shot down or damaged aircraft are not simply lost to the ocean. Many are recovered, repaired, and returned by the same processes that put them into the air. McCampbell becomes the Navy's top-scoring carrier ace, not only because of his marksmanship and nerve, but because he operates inside a force that can keep him supplied and supported. The kill tallies that accrue to pilots like McCampbell and Eugene Valencia are symptoms of a larger machine at work, a production, doctrine, supply complex that multiplies individual effectiveness. Japanese aces continue to fight fiercely. Warrant Officer Hiroyoshi Nishizawa and others still demonstrate extraordinary flying skill in isolated engagements. But high-quality pilots are finite, and training pipelines cannot be rebuilt overnight. The attrition of experienced flyers, the shortening of flight training curricula, and the gradual erosion of maintenance and supply all coalesce into a structural disadvantage. By late 1944, Japan is producing aircraft, but not at the scale, consistency, or repairability that the U.S. system can sustain. That gap between design brilliance and systemic capacity becomes an increasingly decisive fault line.
The next campaign to reveal that fault line is Leyte Gulf in October 1944. The battle is many things: a strategic attempt to return American forces to the Philippines, a cataclysmic naval engagement, and a demonstration of how air power underpinned by industrial throughput can influence fleet actions.
In escorting and defending convoys and carriers, Hellcats perform a multitude of tasks: combat air patrols to repel incoming raids, strafing and interdiction of enemy aircraft operating from land bases, and the delicate business of protecting slower logistics vessels. When carriers launch their wings against enemy formations, they do so confident that replacements exist in the pipeline. If a squadron suffers losses, replacement pilots and aircraft are arriving in the weeks after the fight. Leyte also shows what happens when desperation collides with diminishing options. Faced with unsustainable losses, Japanese leadership initiates and expands special attack tactics, kamikaze operations that trade aircraft and pilot for the chance of a catastrophic strike against ships. Vice Admiral Takejiro Onishi is often identified with these efforts. Whether as architect or as an emblem of a desperate choice, the program's expansion is evidence of the strategic pressure Japan faces. Hellcats on cap duty, flying above task groups, become critical last-line defenders against these attacks. Their speed and firepower make them effective interceptors of suicide aircraft, but they cannot remove the human tragedy of a tactic designed as a deliberate sacrifice. Watching these changes from the factory perspective yields another insight: repairs and returns are as important as production. A Hellcat holed by flak and slammed onto a carrier deck can be patched, stripped, and sent back to a depot for more thorough overhaul. Mechanics on forward airstrips and on carriers improvise and cannibalize when needed. Whole aircraft become stores of spare parts. Bethpage and its subcontractors keep supplying the parts that make those repairs possible: spar fittings, replacement control cables, engine components, gun barrels. Again, the emphasis is on predictability and interchangeability. The parts fit, the manuals tell the crew what torque to apply, and a plane that might have been written off in a different logistical regime returns to the war. The human stories threaded through these cycles are often terse and resigned. Veteran accounts speak of one more sortie and the other half of the equation, the unseen work of armorers and sheet metal men. Oral histories record again and again how pilots trusted their machines more when they knew a shot plane would not necessarily mean a permanent loss. This trust is not arrogance. It is a hard-earned confidence that lets pilots press engagements, to a degree, and contributes to operational effectiveness. Conversely, Japanese pilots who watched wingmen fall without the assurance of replacement felt an erosion of morale and tactical flexibility. The cumulative effect of production, doctrine, and attrition becomes stark in operations into 1945. Okinawa, the attritional high watermark of the carrier-based air war, turns the Hellcat into a platform of many faces. It is a fighter that escorts strikes, hunts interceptors, and defends ships from kamikazes. Hellcats intercept incoming raids with a combination of energy tactics and sheer volume of fire. The psychological strain on both sides intensifies. For American pilots and crew, the unrelenting tempo of sorties creates fatigue and stress. For Japanese pilots, the shrinking margin for error and dwindling reserves of trained personnel eliminate the luxury of experimentation in tactics. Throughout these years, the notion that numbers matter as much as quality pervades after-action analyses. The Hellcat's influence is not a single, clean causal chain that leads inevitably to victory. It is one element within a web of advantages: vast industrial capacity, improved doctrine, superior logistics, radar-enabled command and control, and the ability to replace men and machines. The narrative of American success in 1944 through 45 is therefore a composite story. It is about the aircraft, yes, but also about the people who made them, the men who repaired them, and the systems that coordinated their use. Technical trade-offs continue to draw debate among engineers and officers. On paper, wing loading, power-to-weight ratio, and armament balances define performance envelopes. In practice, the interplay of these variables with maintenance realities and mission demands lead to different judgments. The Hellcat's designers accepted higher wing loading than the Zero did. That decision yields disadvantages in tight turn scenarios, but brings advantages in speed and handling at combat energy. The R2800 engine, a powerful, reliable radio, gives the Hellcat reserves of horsepower that translate into climb rate and acceleration. Exactly how many precision parts the R2800 required in total, or the precise count of components that went into a Hellcat's assembly, R2800 parts count, indefinito, total production parts count, indefinito, are matters for archival verification. What matters narratively is that the engine's robustness and the plane's armor change survivability math on the battlefield. Survivability changes tactics. Fighters that can absorb damage will not be forced out of action by a single burst of fire. Combined with concentrated burnsite fire, that survivability means that engagements are shorter and often more lethal in a single pass. For the Japanese, whose doctrine emphasized endurance in dogfighting and superior maneuvering, the psychological effect of facing opponents who could take punishment and survive is profound. Veteran testimony describes a sense not merely of physical danger, but of a shift in the terms of engagement. Dogfights are no longer about outturning an opponent. They become about denying the opponent a choice. This shift is visible in training adjustments and in the language of debriefings. Squadron briefs start to emphasize altitude discipline, energy retention, and the timing of attacks.
Fighter division tactics evolve toward mutual support and covering arcs, where two or more fighters work to trap an opponent within a vertical envelope it cannot escape. Graphics and drills that had once been theoretical become practical staples. The fleet's air officers incorporate feedback from the line into doctrine quickly. When a new tactic proves effective at intercepts, it is written into the next brief and trained hard. This institutional agility, the speed at which lessons learned in combat are turned into new standard operating procedures, is itself a kind of industrial advantage, one that dovetails with material production. Yet, even as doctrine adapts, the limits of systems show through. The Japanese response to attrition is often innovation under pressure, new aircraft types, modified tactics, and the embrace of desperate measures. The kamikaze program is the most tragic and visible of these responses. It changes the character of naval warfare. Ships named for the thinness of their armor find that no amount of ruggedness is sufficient against a determined human weapon. Hellcats, however, prove their worth in these conditions. Their speed and armament make them effective interceptors, and their presence on cap reduces the number of successful suicide strikes. But the cost remains high. Every intercepted kamikaze is also a human life stopped before it reached its grim objective. Victory in this terrain is always expensive. As the war winds toward its conclusion, attention turns not only to battle damage rates and sortie counts, but to what the captured machines can tell about opposing technologies. When the Americans occupy airfields and shipyards, technicians and engineers gain the chance to inspect Japanese aircraft, and, conversely, for Japanese engineers to see captured Hellcats. In Itsugi and other sites where seized aircraft are pooled, Japanese technicians examine the Hellcat's construction and systems. Jiro Horikoshi, the designer of the Zero, and other Japanese aeronautical minds confront a reality that many had already intuited. The Zero was an elegant and highly effective design for the early years of the war, light, long-ranging, and superbly maneuverable. But Japan's industrial base had not been shaped to sustain a prolonged, high-volume conflict of attrition against a foe with far greater manufacturing depth. The Hellcat's superiority in 1944 and 1945 is therefore as much a product of American structural advantage as it is of engineering choices. Post-war assessments by both sides echo the same mixed conclusion.
American technical evaluations praise the Hellcat for its ruggedness, its ease of maintenance, and the successful integration with carrier doctrine and logistics. Japanese retrospectives mourn the loss of experienced pilots and the inability to replace them, even while acknowledging the skill that created designs like the Zero.
The final judgment is not a simple one-liner about better pilots or better planes. It is a recognition that war in the mid-20th century is, to a large extent, industrial in character. An aircraft's value is measured by the sum of its engineering merits plus the capacity of the society that builds, repairs, and deploys it. In the years after the conflict, museums and archives display Hellcats as proud artifacts of technological and industrial achievement. Curators point to stamped part numbers, to the rugged landing gear, to the generous gas tanks shaped to extend a carrier-based fighter's reach. Scholars studying those airframes emphasize another point. The Hellcat story is inseparable from the people on the shop floor who made each fuselage and from the logistics teams who kept them flying. Oral histories collected from Bethpage machinists and assemblers stress not a desire for glory, but a weary competence. They were, many said, simply doing their job, and the scale of their combined labor made a difference. There is a moral complexity to the narrative that refuses simplistic interpretation. The Hellcat helped produce lopsided outcomes in the air war. It also contributed to campaigns that cost thousands of lives. Industrial superiority did not remove the suffering of war. It reoriented its mechanics. The choice to build robust, maintainable, and producible aircraft was a strategic one, but it was made in a context of desperate geopolitics and grim human choices. That ambiguity stays with any sober retelling. Returning to the factory one last time offers a tidy, modest image. A Hellcat rolls out under fluorescent light, its paint still smelling of enamel. Its propeller-covered crate now empty where an R-2800 once sat. A mechanic slaps a placard on the canopy, noting the passing inspection and the name of the pilot who will fly it first. For the men and women of the plant, the job is never about the glory of a single sortie. It is about a string of small, exact acts repeated enough to create strategic effect. For a world watching the results, that string of acts looks like power multiplied. The aircraft that Japan once laughed at became, by virtue of a factory and a supporting system, a tool central to the Allied effort to dominate the Pacific skies. In the end, the Hellcat story is a compound one. It is about aerodynamics and engines, yes, but also about charts, crates, manpower, and doctrine. It is about the sober arithmetic of production and repair, about the tactical innovations that made mass-produced aircraft more effective, and about the human cost paid on both sides. The laughter of 1943 is a historical detail that underlines a larger lesson. In industrialized war, the edge often belongs to the force that can marry engineering choices with a systemic capacity for sustainment. If you want to explore the archives, pilot diaries, and technical reports that shape this account, the description includes primary source links and a reading list with production records and squadron histories. For more deep dives into the machines and the systems that shaped the 20th century battlefield, watch our next video on how carrier aviation transformed naval strategy. And consider subscribing for more documentary analyses built around factories, fleets, and the people who made them run.